So, wow, it's a lot of you out there. Good morning. Just want to say for those of you in the back row who are like in Northern Virginia, we love you too. I have a lot of images that I want to share with you, so those of you who are sitting on the sides, you may want to come toward the middle, especially you guys in the corners. You don't want to sit with this thing right in your face. Yeah, the big shift. So I've been thinking about change for a long time, and I want to tell you some stories about change. First, a question. Please raise your hand if you're an engineer. Wow. So like everybody in this room, you have to be an engineer. You're not allowed in the room. I hear that engineers like graphs. Please raise your hand if you like graphs. Oh, that's pretty good. All right. Well, so let's look at some graphs. That's a pretty cool one. Wow. Hey, AV guys, the whole image is like shaking. It's going to give people a headache pretty soon. We got to maybe do something about that. Oh, there's another graph. Wow, that one's interesting. See if you can figure out what these graphs are. Yeah, that's definitely better. Thank you. All right. Well, that's two graphs in one. That's two pieces of information. Makes sense, right? Everybody's clear about what it's saying? Oh, there's another one. Little black triangle. What does that mean? We don't know. They all have a different grid behind them, too. What's up with that? This one has an arrow on it. Wow. That means something. Clearly, it's very important information. And you're getting it all, right? It's like osmosis, right? When you were in college, when you were exhausted, you'd stick the textbook under your pillow and say, God, I hope I get this by morning because I got the test 8 a.m. and I'm exhausted. Oh, here's another 2 for 1. All right. So here's what they all were. We just looked at 9 graphs. I am going to tell you what they are in just a second. But I want to set some context. So Barclay mentioned this book that I wrote called The Big Shift. The Big Shift is about how the world is changing really, really fast. Here's another way we can look at it. Whoa, all at once. You like tic-tac-toe? We can do that too. Boom, boom, boom. 1, 2, 3. We win. No X's and O's. It's just lines. Oh, we can go down too, or we can go diagonally. All right, so what do all these graphs have in common, right? You all know this. They're exponential. So exponential is a word that we can use to describe the times in which we're living. This is the way the world is now. Definition, just a sort of a casual definition, repeated doubling in a fixed time frame. So you have a fixed time frame, and it keeps doubling within that time frame. It leads to very, very rapid change. So let's look and see what those graphs were. Those graphs are all important in my view. So this one is concentration of CO2 in the atmosphere, and you can see we have the industrial era, we have the foundation of global warming. And the line is scarily pointing up. Another very interesting graph, this is the human population from the year 10,000 BC until now, so 12,000 years of human history. This is to scale. So that vertical part of the line, or nearly vertical part, that's the industrial era when the population boom happened in the world. That's kind of interesting. This one is actually even perhaps more dramatic than the last one. These two graphs. So the black line represents the human population. You can see what I think is going to happen. And the red line represents the robotic population. Within a few years, there will be potentially 10 robots for each of us in the world. And they'll be doing work for us. So there's a question that's all in the back of our minds, like, well, what are the people going to be doing if we got all these robots? This one you can see is very technical, the label on the vertical axis. This is the number of computer chips in use globally. And the little triangle in the black line, or where it's gray on the right side, that represents current time. So we're just at the knee of the curve, where the explosion of computer technology into society. Here's that one with the arrow. That's the growth of knowledge. So knowledge is doubling very, very fast. You've seen the statistics. You know, it used to take 10 years and then 5 years, and now it's, every few months. And with all the sensors and stuff that you guys are putting out into the world, the amount of knowledge or data that's available is growing exponentially. It is nearly a vertical line now. So some of you are possibly working on the technology systems that are going to help us to manage all that data because we have quite a lot of it now. Some of us are getting older and we're starting to spend a little more money on healthcare. Healthcare is now about 18% of USA GDP, lower in most of the other countries of the world. This is a big problem for people here in Washington trying to figure out what to do about US healthcare, Social Security, Medicare, et cetera. This one looks very similar to another graph. This is GDP. So you can see the industrial era has been this amazing creation of wealth around the world. However, with all this wealth, we've learned how to get into debt. So the red line represents the accumulation of debt on a global basis. The gray line is GDP. You can see the time frame's a little different. Here I was looking at, I'll go back. This is from 1700. This is just from 1980, so the last 30 years. So currently, global debt is about 3 times global GDP. So I don't know if you guys are into financial engineering, but you can see that this is going to present a problem sooner or later. So again, these are all exponential trends, and they have a great deal of influence on what's happening in our world. Certainly, a lot of the conversation here in Washington, D.C., between the White House and the Capitol building. You know, how are we going to manage in a world which is changing exponentially? So these are the driving forces, and there's more of them, obviously, but these are some of the very important ones. Now, here's another one that is probably very close to many of your work, or the work that many of you do. This is actually a double curve. The ascending curve represents computer chip capacity. The descending curve represents cost, and of course we know that as Moore's law. We can also think of that as a double curve, so we call it the D curve. D happens to fit very nicely into that curve. D for double, digitalization, disruption, driver of change. So a great deal of the other exponential curves exist as a consequence of the phenomenon that Moore's law describes, which is this rapid doubling of computer chip capacity over the last 50 years. So here's a simple example of that. 1 gig flash drive would have cost you about $8,000. Now it's worth about $1. So in 12 years, an 8,000-fold price performance improvement, which is pretty impressive. So those of you who worked on this technology, thank you, well done. Now let's see if we can extend that same thinking or that same logic backwards. So if you had an iPhone in 1976, what would that computing power have cost you? Right, so this is running that same curve backwards to 1976. So I'll just give you, I'll give you 4 possible prices, and then we'll do a little show of hands to see what you think it is. So again, it's not obviously the phone, because that much computing power would have taken up a little bit more room than this phone would take. Was it $10,000, $100,000, $1 million, or $1 billion? So let's do a little quick voting. Who thinks it's number 1, $10,000? Please raise your hand. No one raise your hand. Please, don't do it. Don't do it. Any takers on 100,000? Nope, don't do that either. Good. Million? Anybody think it's $1 million? Yeah, we get a few takers on that. And then $1 billion? All right, well, so you guys have been doing your homework. That's great. We'll get around to the answer in a couple minutes. No, you don't have to text it in or anything. I'll just tell you. But I want to explore a little bit about what's been going on with this. Like, what does that mean? So, those of you who are Catholics may recognize this. This is a photograph taken in Rome in 2005. And this is the inauguration or the welcoming of a new pope. So when the pope dies, those of you who are familiar with Catholic ritual, the cardinals get together in the Sistine Chapel, so they kick out all the tourists, and they get to be in there by themselves. And they vote on who's going to be the next pope. And it usually takes a lot of ballots, and so they burn the ballots, and they send up black smoke out of the chimney of the Sistine Chapel. And then when they agree on who the pope is, they send white smoke out the chimney, and the faithful from all over Rome come because they want to meet the new pope. This is a very important thing in Catholicism. So here they are in 2005 waiting to meet the new pope. And you can see this one early adopter down in the right-hand corner. I circled it. He's got a cell phone. He's holding it up to take a picture. Now, the pope who was inaugurated in 2005 retired in 2013. That's unusual. Usually they stay in until they die, but this guy decided that he needed to retire. And so the whole thing happened again. Well, what happened between 2005 and 2013 is that very good, you all left right on cue, thank you, that was perfect. So the world became digitized, and it really started in 2007 with the introduction of the iPhone. So we call this the digital disruption. Right, so we're living in this era of digitalization. And it's happened very insidiously. Like, you remember, some of you, when you were in college, there was no internet, there was no cell phone, there was no smartphone, you know. But as soon as it came out, it was so useful that we adopted it very, very quickly. So we've taken to this technology very easily. And of course, your field has perhaps taken to it more easily than any other field. So now we have the digitization of manufacturing. We have robots building cars because they can do many things better and more safely than humans. So maybe you came here in an Uber, right? Digital technology. The digitization of the whole phenomenon, the relationship, all of transportation. Speaking of transportation, we have the Google car, right? Very cute little car. It's designed to be cute. It's intended to be non-threatening because, of course, self-driving cars are kind of a scary thing. Many of you are in aviation. You know that these airplanes are now digital, so digitalization of aviation, it's a very common thing. Warfare, some of you are working for the DoD. Cyber command, of course, is the digitalization of conflict. This is the way that we're thinking about warfare and conflict now. But also things like farming. So this is the cab of a modern tractor. Tractor costs you about $500,000. John Deere would be happy to take orders. I think they have a booth in the trade show. If you've got 20,000 acres of corn, this is what you need. This guy's got 7 displays in his cab, and he's looking at 22 different metrics that are being measured on a real-time basis. So this is the digitalization of agriculture. Right? Agriculture is a high-tech profession. There's now a restaurant in Boston that has robots in the kitchen. It was started by some guys, and they did the prototype in their MIT frat house basement. So, you know, we don't know if it's going to work. It could be the next McDonald's. There could be one of these things all over the world. It could be the prototype fails. But we know sooner or later it will not fail. Sooner or later that the robots will be doing the cooking. You can actually buy a robot. It'll put it in your kitchen. It will observe you making a meal, and then it will be able to make that meal the next time you want that same meal. Some of you are in automotive engineering. You probably know that Ford is already using holograms for automotive design. So obviously a hologram is a lot quicker than building the clay model. Speed is very important, obviously, in the automotive industry. You've maybe heard about drone delivery. So this is a photograph of an Amazon drone, which is in development. I gave a talk in New Zealand last October, and I showed a slide like this, and they said, well, we're already doing that here, mate. Domino's is delivering pizza with drones. Oh, I didn't know that. And there's a company called DT.com. They're delivering packages. They're an Alibaba competitor. They're in China, so they're like Amazon. They're delivering packages to 100 villages in China with drones every day. 3 or 4 packages get delivered every day. There's a person on the ground in the village who receives the package and then distributes the contents to the people who ordered stuff. So this is clearly coming. It's already come. Creates very interesting things to think about. The world is changing. Speaking of change, we all heard of Bitcoin, right? Right. So who can explain it to their parents or their grandparents? Right? No, we can't. We have to have. Oh, you can, right? Of course. Yeah. Our high school award winner raised her hand. She understands it. Well done. If I have a few extra minutes when I'm done, can you come up and give us the explanation? Yeah, so we know it's coming. We know it's significant. We're not sure what it is. It's like Bitcoin, well, there's a blockchain behind it. What's a blockchain, blah, blah, blah. But in Kenya, for example, they're already using digital money. Half of the people in Kenya are using digital money. It's called M-Pesa. M for mobile, Pesa is Swahili for money. What they do is they swapped airtime. Airtime became a currency, and the cell phone companies realized that, wow, we had created a currency, and so now it's officially recognized. There's digital currency in all over Eastern Africa. So really what we're talking about is the digitization of all these industries, everything. Everything we do is now somehow connected in the digital world. Right? So it's been very disruptive for industry. Everything is digitized, which means that everything is connected to everything, which means that the world is becoming much more complex. And it's only going to become even more complex, which is sort of the theme of what we're talking about today. So we need a definition for complexity. I'll give you, again, this is a non-technical definition. Complexity is when behaviors emerge because of connections and interactions between the elements of a system. Right, so we got system, we got your profession in here, systems engineering. Right, so lots of parts, lots of elements, and they're connected somehow. So is this what we're talking about? Lots of parts and elements, they're connected. Probably not complexity. This is technology. Wow, lots of parts and pieces, but not connected in a particularly useful way. This, on the other hand, is complexity because there's lots of components that are connected in an incredibly useful way, which it gets us around to the answer to the question that you raised your hands about. And it turns out that the correct answer is 3.2 billion. Yeah. So I read this, somebody at AMD calculated it fairly recently, and it was published online, and I read it, and I give a fair number of speeches, and so I gave a speech about a year and a half ago. It was a smaller group than this, small enough that the group could heckle me. And so somebody in about the fourth row raised her hand, and she was visibly very upset with this, and she said, "That's not right." I said, "Oh, really?" She said, "Our company had a Cray computer in 1976, and we only paid $20 million for it, so your number's got to be wrong." And so, I'm not a computer scientist, so what was I going to do? I was going to blush, first of all, did that. Then I was going to apologize, I did that. And then I might as well have just ended the speech right there, right? Because nothing that I said after that was anybody was going to believe me or pay attention to. But I carried on through, and I finished it. And then I went and did a little research. And so here's a picture of a Cray 1 in 1976. She was actually wrong. It only cost $9 million. It wasn't $20 million. And I contacted some tech friends of mine, and we did a little research online, and we discovered that your iPhone, which you probably have in your pocket, this is mine, is 1,000 times more powerful than a Cray computer. Right? And unfortunately, she hadn't left her name and number, and so I wasn't able to call her up. So 1,000 times, so we could not fit 1,000 Crays in this room. It might take all 5 levels, all the way up to DEFCON 0, to get all 1,000 Cray computers, right? But that's what's in your pocket. So you have a $3 billion computing device in 1976 terms in your pocket. It's interesting. It's changing the world. Yeah, so there it is, 1,000 times more powerful. So now let's think about the future, because that's really what we're very interested in. How much more powerful will your phone be in 9 or 10 years from now? Well, if you know the logic of Moore's law, where computer power is doubling roughly every 2 years, you just 2 to the 10th, and you get roughly 32 times more powerful. So what are we going to do with a device in our pocket that's 32 times more powerful than this? Well, it's not going to be in our pocket for one thing, because it's going to be right here, or it's going to be a transdermal chip, or it's just going to be the environment. We're going to be living in computer environments. Maybe it's going to be clothing or my tie. By the way, if you want to look for me afterwards, I'll be the one in the tie. So this is shaping reality. This is shaping reality. So we do a lot of consulting for businesses, and it's very difficult to convey to business leaders how much change they're going to have to be dealing with in the next 5 to 10 years, because it's happened very insidiously, as I said. So we show this curve, and we say, well, what's coming is this new reality, and we think of it as a digital danger zone. Right? Because what are you going to do? You're going to go to college, you're going to learn how to, maybe you'll get your PhD, and then you're going to go and disrupt some company somewhere. So all these young people are studying about how to disrupt the companies that the rest of you are working for. So for you, it's a digital danger zone. for her and her peers, it's the digital opportunity zone. So this is what's coming. Now, we'll get back to this in a little bit, in another few minutes. We'll cycle back around to this question. But first I want to make a bit of a digression and look at one of the other graphs, which is really important, and that's about the human population. So before I showed you from 10,000 BC until now, so 12,000 years of history, now we're looking at from year one. So that's the curve. So this is the last 2017 years of history. Now what happens if we project forward a couple hundred more years? So I'm going to show you 4 options, and again we're going to do a little hand voting just to see what you think is happening. Who thinks that the population is going to continue to expand exponentially? That's option 1. Option 2 slows down a little bit. Option 3 stabilizes. Option 4, those of you who are very pessimistic. So let's see a show of hands. Who thinks that number 1 is the best prediction? Oh, very interesting. Okay, you were listening before. Option 2? Okay, not too many, a few hands. Option 3? A lot of people think that. Option 4? Yeah, okay. So we'll get around to giving you the answer shortly. But first I want to talk about how we actually have an answer. Like, how do we know what's going to happen? Well, so we're now talking about the study of demographics. So if we think about the future, right, we have technology on one hand and we have the population on the other. Right now the population is roughly 7.5 billion humans. Not sure how many robots there are, but we'll just count the people. But if the population was to double to 15 billion, that would have massive influence and impact on all of us, or even more to 30 billion, right? Or if it was to contract to 3.5 billion. The population, in other words, is a very important figure because it defines so much of the reality that we have to deal with in the world. So we'll look at one population graph. This is a country, not a company, a country, millions of people. You can see from 1875 until today, orange line is today. The forecast for the population of this country is that the population is actually contracting. So think in your mind, think maybe you know what country this is. This is Japan. And it's not just Japan. In fact, there are between 40 and 60 countries in the world where the population is actually declining. And so, of course, being engineers, you're asking a lot of questions and you're saying, why? Why would the population of Japan be forecast to decline? And the answer seems to be urbanization. Right? So it turns out that when we live on farms, children represent what? Labor. Do we pay them? Free labor, right? So having children becomes an economic asset to a family. If you have a big enough piece of land on a farm, a child is an economic asset, produces more than they consume. In the city, is the child an economic asset or a consumer? Yes. I come home from a trip and my children don't say, "Hi, Dad, how was your trip? How was your talk? Did you meet some cool people? What did you learn?" And they say, "Hey, Dad, I need 20 bucks. "Oh, no, it's inflation. Sorry, Dad, I need 100 bucks. Right? So in the city, we have a completely different logic. The logic of parenting in the city as a financial decision is we typically have fewer children. Turns out that Japan is the most urbanized country in the world. And the population growth rate of Japan is negative. Generally, for a country to maintain a stable population, it requires 2.1 children per woman, and in Japan, it's about 1.2. And if that trend continues through the rest of the century, then Japan will have half the people in 2100 roughly than it has today, which for Japan will be a disaster because it will no longer be a world power, and it'll be a country filled with old people. This is a picture of Tokyo, by the way. So what we're talking about is how connections create complexity and how complexity creates unpredictability. So all these exponential phenomenon are based on connections. They're creating an incredibly complex environment in which we live, physical and conceptual and intellectual. And that's leading to incredibly high levels of unpredictability. So what we say is that complexity essentially creates counterintuitive behaviors. You know, when Japan started to urbanize, the prime minister or the people in the leadership didn't say, "Wow, this is going to be a disaster for us. We got to keep people on the farms. This urbanization thing it's got to stop." right? I mean, we're going to be destroyed as a country if we keep urbanizing. No, we didn't understand that. So it's counterintuitive. It's not what we expected. Complexity creates unexpected behaviors. That's what it does. So here's a graph of world population, blue being rural, red being urban, black line being today. That's what's happening globally. People all over the world are moving into the cities. So that tells you something about what we should expect of the future population growth rate. If everybody is living in cities and people in cities have fewer children, then the population actually might decline, which is actually what's forecast to happen. So there's some interesting numbers. Roughly 4 billion more people will be living in cities by the end of this century than are living in cities today. So from a systems engineering perspective, designing cities that work actually becomes a very interesting prospect. So here we have a graph of China. You can see 2010 to 2030. There's 3 population groups here. I'm not going to label them. You have to figure out which population segment is which. And then here's Japan from 2010 to 2030. And you can see that where China is heading is where Japan is now, is what this graph shows. So the red line represents working age people, those who are producing and paying taxes. The middle line is youth, and the gray line is elderly. So you can see by 2030, the elderly will be the predominant population in Japan. And by 2060, it'll be the predominant population in China, if things don't change. And so those of you who are worried about the relationship between the US and China can take some solace in the fact that in 30 years, China is going to be dealing with the same population and economic dynamics that Japan is dealing with now. So we have to wonder, is this a catastrophe or is this a boon? Well, it could be a boon in the sense that it means that less resources might be consumed, but it could be a catastrophe for these two countries in terms of their relationship in geopolitics. So that's the world. So here's the answer to the question. It was number 5, so a trick question. The population is forecast to decline. And that means that we're all getting older, and it means that we have to create essentially a new economy. So we have an economy that's designed for boom, and we're moving into an economy that's designed for something else. So those of you who are systems engineers interested in the economy, here's your chance. So what we are is we're at a turning point globally. And so the reason I wrote this book, The Big Shift, is because I began to understand this, and I said, wow, this is pretty interesting. And so here's a little evidence for that. This is the population growth rate, and you can see over the last few years, the growth rate has started to slow globally. So we now have a sort of a model of human history. We can say, well, complexity created the industrial era, right? So we had agriculture, we got better and better at agriculture, we created industry, and now we're moving into this third thing, and it's even more complex, we don't really know what it is. We could say phase 1 is the agricultural era, phase 2 is 200 very short years of industrialism, and phase 3 is what we're moving into. So of course the question is, how much complexity can we handle? If we're continuing to create more and more complexity, what does that mean? Interesting study by some anthropologists. They looked at the growth of complexity in historical civilizations, and they discovered something called declining marginal returns on complexity. They said, you can see the vertical axis, the benefits of more complexity. Complexity creates benefits, but then at a certain point, things become so complex that it becomes more costly. And this is what leads to civilization collapse. So it's an uh-oh moment. All right, so what's the next slide going to be? We're at the uh-oh moment. Potentially, right? What's the solution? Voila, magic, innovation. We're going to innovate our way out of this. Now we need a definition for innovation, so we'll take a highly technical one. Right, so some genius came up with this definition. Right? Well, it's a discovery process. We don't know, right? If we knew what we were doing, we'd probably call it engineering. But we don't know, so we call it innovation. And then actually a genius did come up with this. This is Einstein. Right? So yeah, he really was a genius. Okay. So what does innovation do? It creates complexity. And it raises the question, what will emerge, right? If complexity leads to unexpected behaviors or counterintuitive behaviors, then what will emerge? Emerge is a very important concept. Those of you who have studied model-based systems engineering, they talk a lot about emergence. But innovation is also a strategy to manage complexity. So there's our definition. So I want to give you a case study now from your field, but a story that you possibly haven't heard yet. This is a story of Apollo 13. You all saw the movie, right? Everybody has seen the movie? So you know how it ends. I want to tell you how it got there. This is a story that was shared with me 20 years ago by a senior engineer at NASA named Dr. Ken Cox. And I interviewed Ken for a book that I was writing 20 years ago. And we became friends and we worked together for the next 16 years until he died recently. And Dr. Cox was one of the critical thinkers in NASA. And he told me this amazing story, which I want to share with you today. So this section of slides is a combination of his slides and a few that I've added. So this is a presentation that he had given many times. He said in order to do this, which was to get astronauts onto the moon, we had to design and build this. And you can see there is a human next to the Atlas. And we still haven't built another rocket that's as powerful as this, although SpaceX has aspirations to do that. The way the system worked was to fly to the moon, you had to have these three elements. So we had the command module, the command service module, the lunar module. So this is Ken talking, he says, who were we? We were thousands of engineers and scientists. We were in 8 NASA centers. We were many, many contractors and university labs all over the country. It's a massive effort. And so now, obviously Apollo 11 and Apollo 12 were very successful. Apollo 13 had a different story. So we have an emergence, which becomes an emergency, right? So you know the oxygen tank exploded. And so the message is, excuse me, we have a little problem up here. And so, again, this is one of Dr. Cox's slides. He said, so the LEM was alive, the command module was comatose, and the service module was completely dead. Now, the big engine at the back of the service module is what makes the whole thing work. Because, and I'm not a space scientist or an astrophysicist, but so those of you who are can correct me later, but not in public. But when you send a rocket to the moon, it's going at a velocity that it will not enter orbit into the moon unless you fire the big engine at the back. And when you want to return to the Earth, same thing. You have to slow the craft down so that Earth's gravity or moon's gravity can grab it. But you can see the craft was completely dead. So what happens? Well, so what we have is, again, we have an example of this complexity, connections complexity, unpredictability problem. We have potentially discovered the marginal return on complexity, and so we wonder, will the astronauts make it back? Legitimate question. Well, so the story that I want to tell you about what Dr. Cox did is he was a young man, started working for NASA in the early 60s. He was still in his 20s. He didn't yet have his PhD, but he was one of the few engineers in the world who had worked on the digitization of spacecraft. He worked for Martin Marietta in Colorado working on ICBMs. And so he was a very young man, but he was given in 1964-65 the job of being the head engineer for the digitization of Apollo. He was probably at that time about 28, right? So you can imagine a 28-year-old in charge of something that's really pretty important to the success of the space program. Now the Gemini and Mercury, or the Mercury and Gemini capsules were analog flight systems. But digital technology was coming along to the extent that NASA realized that they wanted to see how much digital technology should be put into the avionics for Apollo. So Ken was hired to figure that out. There were 2 major contractors working, as you can see, Grumman and Rockwell, now North American. And they said, well, no, we got to keep with the analog system. We got to go with the tried and true. And Ken said, well, yeah, but digital technology can give us so many more options. And the contractor said, yeah, but we got to stick with the tried and true. So they had this debate for a while. And eventually they started to work on the digitization anyway. And software at that time, the software in Apollo was managed by a control board. So there was a control board, and every time you wanted to do a design change to the software, you had to go before the control board and make the presentation. And so they had worked out the design so that both the LEM and the command module and the service module would all be digital. And the logic or the rationale behind it was, believe it or not, this is what Ken told me, that if there was a problem with any one of the craft, as long as one of the craft was working, you could interconnect them if they were digital, but you could not do that if they were analog. If there was a problem with any craft in the analog system, you were basically hosed. But if they were digital, then you could interconnect them and you could control any one from any of the three. And so Ken took this proposal to the software control board. This would have been about 1966, 67. So he presents the logic of it, and the control board is very respectful, and they say, Ken, you know, you've done a great piece of engineering work here, but you haven't convinced us that there's a potential problem. We don't see a credible scenario that there's a problem, so we're going to turn down your request. Now, Ken's telling me this story in about 1998, so this is 30 years later. And he says, but it was the right thing to do. I was so upset. He has a southern accent. So he was like 30 years later, he's still remembering the depth of emotion that he felt about this. And so after the meeting, he's leaving and he's crushed, like, we're not doing the right thing here. We're not doing the right thing. This is crazy. And so he's leaving the room, and he said, Chris Kraft, who was head of the control board, this is before Chris Kraft ran Johnson Space Center. He's, Ken, come over here. And they get over in the corner, and Chris Kraft says, I had to say that for political reasons, but I want you to go ahead and do it. Now, none of you have ever experienced anything political in your work, I'm sure. Right. So they go ahead and do it. The software is coded in. The coding work was actually done at MIT. And Ken's a very astute guy, even in his now probably 30 at this point. And so 3 or 4 months later, they have the code worked out. They go back to the control board, and this is what Ken says. Now remember this. This may be useful to you. Ken says, well, you know, last time I was here, I told you what we thought we ought to do, and you said we shouldn't do it. But I want to just tell you, I just want to be right up front with you. I want to tell you, we went ahead and we did it anyway. And we can take it out, but it'll cost you time and money to take it out. And so Chris Kraft says, well, Ken, I guess we just might as well leave it in. All right. So this is the result. If they had not done that, the astronauts would still be heading off towards Alpha Centauri. Right? So Ken had to, and Chris Kraft had to manipulate the politics of the situation to do the right thing, to embed new technical capabilities into a tried and true technology. So if you ever go to NASA and you tour Mission Control, which because Ken was a friend of mine, I got to do, you'll see this plaque in Mission Control. It's the old Mission Control room that they don't use anymore. And you can read what it says. This mirror flown on Aquarius, which was the LEM. It's an aluminum mirror, obviously it wasn't glass. The crew took it out of the LEM and brought it back with them, and they put this plaque, and they put it over the water cooler, right, the water fountain in Mission Control. And they basically said, thanks guys for bringing us back. We really appreciate it. So it's there. Yeah, isn't that an awesome story? So good job, systems engineers. So systems engineering is a strategy for managing complexity, but then we have to ask ourselves, well, what are the boundaries of the system, right? So then that leads to the question, well, how did a defective oxygen tank ever end up in Apollo 13 in the first place? So this is a picture of the assembly building for the command module. So this is another interesting and somewhat sad story. And it's a question about boundaries, which is a really important question for you as systems engineers, because what are the boundaries of the system? Well, so in the assembly building, you know, they would manufacture the components, or they would get shipped in from the suppliers, and they would test them. And the oxygen tank in question, the one that exploded, had been tested as defective. It was known to be defective. And I don't know, one of two things happened. Either it was mislabeled, or it was put back in the wrong place in the warehouse, and another technician grabbed that oxygen tank and put it into the Apollo 13 service module. Right, so it's a boundary question, because if the system is only the vehicle but doesn't include the assembly process of the vehicle to ensure that a defective part which is known to be defective doesn't get put in the vehicle, then the system's boundaries have been improperly defined. Right? So how far should you as systems engineers think about the system that you're working in? Well, we can design the perfect spacecraft, but if somebody puts a known defective part into it because that part was stored in the wrong place in the warehouse, then our systems design has failed. So, touch about politics and about boundaries. This picture I took yesterday afternoon when I was arriving. Here we have a systems design problem as well. This is at Reagan Airport. Here we have 50 people waiting in line for taxis, and here we have 50 taxis waiting to receive them, but we can only load 4 at a time. It's a systems problem. It's like, wait a minute, who figured this out? Doesn't make any sense. So, does systems engineering require innovation? Yeah, of course it does. Innovation is creating value for end users. How do companies feel about innovation? This is not intended to be a direct comment about any of you. And why do they hate it? Because they think it looks like this. Right? Innovation is risky, slow, expensive, unpredictable, blah, 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 blah. Right? It's not manageable. So we have this paradox. We know we have to innovate in order to do cool new stuff and to do the stuff that actually benefits our organizations. And yet we live in institutional structures where innovation is maybe hated. Maybe hate's a bit of an overstatement. Like we love it, but we hate it. We love it when it works, but we hate getting there. Something like that. So some scholars from Japan did an interesting study, and they said in organizations there are 3 types of people. There are idea creators, idea promoters, and so think in your mind, in the companies that you've worked in, like what percentage of the people would you say were idea creators? And what percent would you say were idea promoters? And what percent are, what is the other category? Oh, well, so we got 85% of them are question mark. So let's talk about the question mark people for a second. So what's the role of management? You guys are the best audience ever. Thank you so much. This is so much fun for me. And you know, you laugh, but actually it does make sense, right? Because we can't make profit if we don't have stable, predictable cash flows, and that requires the elimination of variety. This is what Lean Six Sigma is all about, really. It's eliminating variety. So what this says is that 85% of the people in most organizations are doing the right thing because they're enabling us to be successful, and you can see how happy they are. Because what do? There's a word missing there, idea, what? What is their job? Killers, very good. I heard that, right? So those of you who think of yourselves as innovators or idea promoters, right? This is what you're working against. I mean, think about Ken Cox, right? Right? I was the right thing to do. Right? I can still hear him. It was the right thing to do. And yet, killing the idea was also the right thing to do because we have a schedule, we have a budget, blah, 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 blah. So we have this interesting conflict and paradox. And so, of course, the job of innovation is to create the thing that management is trying to kill. So we have this conflict. And why does it matter? Well, it matters because it's the basis of competition, right? Innovation is what we're competing about in the marketplace. If we don't get innovation to the marketplace, we are not going to be successful, right? So it doesn't matter if we're in aviation or appliances or whatever. By the way, speaking of systems design problems, you've heard about the Rolls-Royce engines, right? Complexity. Talking about energy systems, talking about global competition. So innovation is something that we hate. That's a bit of an overstatement, but you get the idea. But it's also mandatory. And by the way, we're living in this kind of world. So yeah, we really have to innovate or we're really not going to be around. So how do we kill variety? Right, well, we have all these different techniques that we use. Right. You can Google it. There's a web page, and it's 101 things that managers say to kill innovation. It's the same list. So change fails, innovation fails because we really don't like it, we don't do it well. So what do we have to do? Well, we have to create alignment. This is the old light bulb, right? So Edison and his team supposedly tested about 6,000 materials for the filament. So what do we want to do in the world of innovation? What do we want to do? We actually want to fail. We want to fail faster, because the faster we fail, the faster we succeed. We don't want to fail on the way to the moon. We want to fail in the lab when it's safe. So we want to do intelligent failure. But if it takes us 20 years to do 6,000 tests, then maybe that's not as good as taking 20 days to do 6,000 tests, because speed matters. So we have to ask more questions, right? This is something that the idea killer people are not usually often that comfortable with. But we can enable and enhance innovation, right? So these are things that we can do to enhance innovation. I have to skip ahead because there were so many things I wanted to talk about. I didn't know how long this was going to take. All right. Let's go to here. So this is the reality that you're coping with, right? This notion of declining marginal returns. You can keep adding more and more complexity, but if it's not adding benefit, it's actually slowing the system down. So what do we have to do? Well, conceptually, what we have to do is rethink about adding the next curve. Right, so this is actually where systems engineering can create incredible value by starting on a new value curve, essentially. And this is where systems engineering and innovation have a great deal of overlap. Society is going to require a new technical infrastructure, right? Because we have an infrastructure designed for a booming population, and we're shifting into an era where we have a declining population, which is going to be one of the major structuring realities of civilization. So again, systems engineering has a great role to play in all that. You'll exploit the power of digital technology, obviously. And what you're going to do, I believe, this is a prediction on my part, is you're going to embed more and more knowledge into the systems that you build. Right? So high knowledge density is really what we're talking about. So I'm coming to the end of my talk. I'm probably already over time. Sorry, David. So what we've talked about is the notion of exponential change, its relationship with complexity, innovation, and systems engineering. And we looked at all these instances of change, and these are all reality. We can't control this. We can't stop this from happening. This is clearly what's happening in the world. So our challenge is to figure out how to make sense of it, how to make it work, how to make it successful for the organizations you work with and for society as a whole. And the thing that we have to be cautious about is that if the exponential curve is a good description of reality, which I argue that it is, right? So this is really what's happening. If we have a mental model that changes much slower, then we have a fundamental disconnect between reality and our mental model. And we also label this slower line the going out of business line. Right? So if your organization, your management thinks that the orange line is a description of reality and we have all this time because things are going slowly, then the most important thing for you to do is to work on your resume, because that's not reality. That's not what's happening. What's happening is exponential change. So the way I describe it is the world is changing. That's what all those exponential change curves are about, plus the S-curve of the population. So we have to change our mindset. We have to change the way we think about the world, because our mental models, many of them are incorrect. And then we need new skills. So just to summarize, if we say that the population curve is defining reality, and there are other ways to define reality, but the population curve is pretty fundamental. It says we're at a turning point in society. Right? So our energy systems are going to change. We're going to move away from fossil fuels. We're rapidly urbanizing. Technology is changing. We're in this interesting, unpleasant political environment. We've got climate change to cope with. Economics is changing. Everything is changing. We're at this turning point. So we think of it as a big shift. Right? And so I wrote a book called The Big Shift, right? Which I brought a copy of to wave in front of you. But I also brought a handful of copies, and they're at the INCOSE Village booth upstairs, I guess, yeah. So you're welcome to check it out. It went live on Amazon yesterday, so if you hurry, you might be the first buyer. but hopefully you won't be the last buyer. I really appreciate all your laughter and your engagement this morning. Thank you so much. It's been a pleasure, and I wish you a great conference.